Everybody, Dave Lindbergh in Hong Kong with another episode of THD Podcast. Today we have a gentleman joining us from Iceland, a company called Treble, specialized in room correction, 3D audio, so helping architects who are, virtually creating the rooms, kind of giving them some instruction on how that's going to behave and what things they can do to make it perfect, and also some other applications into VR, into making people be able to realize what things will sound like in different room environments in the virtual world. So without delay, let's get into it then. So joining us as always, we have Simon Weston in Japan. Good afternoon, Simon.
Evening, in fact, but yeah, afternoon.
Evening.
And probably morning for you, Finnur.
Absolutely. It's 9 o'clock in the morning here in Iceland.
All right. So Finnur Pind, CEO of Treble, thanks for joining us today. We appreciate this.
Yeah, thanks very much for having me. It's an honor to be on your podcast. I've seen many cool names in the audio industry come on before me, so it's a pleasure to be with you.
Okay, that's flattering. We started this as a bit of a hobby, but basically we like to give people a platform to present their technology, something you can't really do so easily without trade shows and such. So we try to do this virtually. So yeah, I always try to take a guess as to what I think your technology is about. So please maybe just walk us into it and tell us about your company.
Right. So I prepared a few slides. I'm thinking maybe I should just go ahead and share the screen already.
Please.
Our company is called Treble, or Treble Technologies, and we have this tagline in Treble: enabling a better sounding world. We think that summarizes quite well what we're about. That is to say, we're developing software, simulation software, to enable various industries to analyze and design sound in a better way than what's been previously possible. So that's kind of the big picture overview, you could say. And so today, or through these slides, I kind of divided them into three parts. I first wanted just to tell you a bit about my own background and how this whole thing came into being. It's coming out of research in the academic world and so on. And then dive a little into the details of the technology and how it works and what are the benefits of it and so on. And then sort of end on a more practical note on where this can be used in practice, and show you a couple of demos and so on. So I hope this is okay. And of course, it's not, I hope not meant to be like a very long monologue of me just talking and you listening. So by all means, if you have any questions or comments along the way, then just shoot them in.
Yeah. Don't worry, it's interactive.
Awesome. Sounds great. I should mention that we're not an old company. We've been around for a year and a half. So it's early stage for us, but so maybe the presentation shows that a little bit, but I hope that's just all right with everyone.
Okay.
So starting with my own background, my initial interest in sound and acoustics and audio technology comes from, I think, a similar place as many other people in this industry, from music. And I was in a rock band back in the day, and my dream was to become a rock star, like so many similar people in similar situation. But actually, I became kind of obsessed with the sort of technical aspect of sound. The guitar effects and the guitar amplifiers and the recording software and all of this stuff. And it kind of got to a point where I was my main objective in life was just to get my guitar to sound as weird as possible. That was a fun time in my life. And how, maybe a normal guitar solo that might sound something like this. This is Jimmy Page from Led Zeppelin here. Maybe not a normal guitar solo. That's a pretty awesome guitar solo from Stairway to Heaven. But anyway, for comparison, my guitar solos, they sounded like this. Basically just a bunch of noise.
That's all.
That was a lot of fun. But for some strange reason that still remains a mystery to this day. There was not a huge demand in the market for these types of guitar solos. So I sort of slowly realized that maybe the rockstar dream was not going to pan out. So I just went all into the technical aspect of sound and into engineering. I studied electrical engineering first, and was working as a software engineer for some time. And then I went to move to Copenhagen. So I'm originally from Iceland, but moved to Denmark to study at DTU, acoustical engineering. So in Denmark, there's a very long tradition for sound and acoustics and acoustic engineering. This photograph is taken maybe 12 years ago during my master studies years.
Okay. Is that an echoic chamber?
Yeah, a reverberation chamber, exactly.
Right. It's something, sorry to interrupt, that's something that a lot of engineers, they don't normally run into. I think at Premium Sound Solutions in Belgium, I found one, but most places only have anechoic. So
right,
a big echo chamber is something not everybody always sees. That's cool.
Exactly. It's kind of the opposite of the anechoic chamber. So this is used, for example, as what we're learning there. This is my longtime collaborator and professor at DTU. His name is Kjell Ho, and a couple of buddies of mine from the study years, where he's teaching us how to measure sound absorption properties of materials. So we have a material sample here on the floor, some rock wool or some porous material, and you essentially measure the reverb time in the room with and without the material, and then you can use some pretty simple math to compute the kind of absorption properties of this material. So that's what's going on in the photo there. And I did my master project together with Bang & Olufsen on kind of room acoustic simulations, and that's how I started to dip my toes into that field, which is sort of my main field, or has been since. And that was quite fun, and I indicated to Kjell Ho, who was my supervisor, that I would be interested in kind of taking that further, maybe do a PhD on the topic or something to continue the development of this exciting field and exciting technology. But there wasn't anything available at the time, so I moved back to Iceland and became an acoustic consultant in the building industry. So I was helping architects design buildings to sound good, basically. This is an example of a fun project. This is a recording studio owned by the Icelandic band Sigurós. Maybe you've heard of them.
Yeah.
So I designed the acoustics of that space together with them, and we see some kind of bass absorbers here in the ceiling and some kind of cool diffusers on the walls and so on. So that was a very fun project. But anyway, while I was in Iceland and doing acoustic consultancy, then Kjell Ho was sort of putting out feelers, trying to get something going on to be able to start a research project on this. And he got in contact with an architect firm called Henning Larsen, which is a sort of well-known architect firm, especially in the Nordic area. This is an example of a building they have designed. It's called Harpa. It's a concert hall and conference center in Reykjavík, Iceland, where I'm right now. And they were constantly running into problems with respect to sound. They would design something that they thought was great, looked great, it had great daylight and all the other things that architects, concern themselves with. But then it kept occurring again and again that they had designed something, and then in the end of the project, or maybe even after the thing was built, they figured out that the acoustics were all wrong. And that could be for a concert hall like we're seeing here, but maybe even more commonly occurring when they design schools, hospitals, residential buildings, etc. So they were kind of very eager to work with DTU, the Technical University in Denmark, to try and develop some technology or some methods that could help the architects incorporate sound as a part of their building design. And Kjell Ho called me and said, "Hey, we have this industrial partner. We got funding. You want to come back and develop some technology?" And I was like, "Hell yeah, let's do it." And that's how, this whole development started.
This idea of the developing the room space or buildings to have good sound. What does that actually mean? Does that mean not too much reverberation, but not none? And
Yeah, exactly. Kind of striking the right balance of having enough sound absorption, depending on the use case. If we're talking about a kindergarten, then your objective is just to dampen the thing as much as possible, right? So people don't go kind of crazy in there.
Yeah.
But if we're talking about a classroom or an auditorium, then you want to have some kind of support from the room, some amplification essentially, so that your speech kind of reaches the back end of the auditorium or the classroom. And yes, and for concert halls, especially classical music concert halls, then you want a lot of reverb because you really want the hall to kind of carry the music. So depends on the use case exactly.
And in terms of this, the science background of that, do you think that it's not extremely well developed? Is it quite a bit of scope to improve simulation tools and things like that?
Yeah, I would say the sort of the fundamentals of what is needed to make a space sound good is quite well developed, but the whole but what is the desired design goal is well known, but how to get there is less developed, and especially these simulation methods. They have some limitations, and which I'll come back to when I cover the sort of technology more in depth, and sort of this whole kind of use towards, for example, architects. Because for them, sound is a kind of almost like a black magic thing. It's obviously invisible. It's very intangible, and sort of designing for that can be quite tricky. So there's not really good solutions for that to make sound more tangible, and that's really a part of what we're trying to do.
Mm-hmm. Okay. Is there kind of a simulation between like the COMSOL people who kind of you can design a loudspeaker and put in all the materials you plan to use in that speaker, and then kind of predict how it's going to emanate sound? And so this is kind of like almost a converse of that, is you're kind of looking to see how all the sound will reverb and such in a 3D structure.
Absolutely. It's very related. COMSOL is a very powerful software that has kind of a very broad range of features to simulate different types of physics. We have, like in a loudspeaker, you have the coupling between the magnetic system and the mechanics and the acoustics and so on. But sort of a challenge with COMSOL is that you cannot really go to these kind of big cases, where you have a full room, because that's a much bigger domain than a loudspeaker, for example. So that's something that we try to address.
Okay, seems like keep going. I think the problem about building a structure, it's no different from somebody giving you an industrial design for a Bluetooth speaker and said, make it sound good. It's always this afterthought of acoustics, which is something that I think everybody talking today would wish people would pay attention at the beginning.
Right. Absolutely. And, hopefully by making it a bit more tangible, allowing people to hear the simulation and so on, which I'll come back to, that will kind of motivate people and to think about acoustics, and then they start understanding the impact of having good sound and so on. So yeah. Okay. One thing I wanted to mention here was so during my master project, we had good success. It went well and so on. But I also kind of learned during that time that this simulation stuff, these computational methods, solving differential equations that describe sound using numerical methods, it's complicated stuff. And we knew a lot about the acoustics and so on, but felt that we were a bit sort of, like short-handed on the numerical aspects. So when we started the PhD project, I thought to myself, there's got to be someone at DTU, this huge technical university that knows numerical methods in scientific computing and so on. And I essentially just Googled and found this guy here in the upper left corner. His name is Alan Engse-Karup, and he has been working for 20 years on developing numerical methods to simulate wave problems, not actually acoustic problems, but for example, what we see here is like water wave problems, so developing advanced methods for this. And then he wanted to come on board, and then he also connected us with another guy. His name is Jan Hesteven. He's a professor at EPFL in Switzerland, who also has been doing wave problems for many, many years. Again, not so much acoustics, but for example, electromagnetic waves, like what we see here. So now we had this kind of pretty powerful team of sort of interdisciplinary team of acoustics experts and architects and these guys on the numerics. And kind of that's the team that came together and started developing this technology that in the end, I would like to argue that we were quite successful. We ended up with something that's pretty powerful, and I'll go into the details of that in a couple of slides. So that's kind of how it started. After the PhD, where we had sort of the academic proof of concept of the technology, we founded Treble, me and my pal Jesper, who was actually in that photograph earlier from the reverberation chamber. So we had studied back at DTU 10, 12 years ago. He had then gone into the hearing aid industry and became a simulation specialist there, was simulating and designing hearing aids for 8 years or something. So I kind of reached out to him and was like, hey, you know a lot about simulation, acoustic simulations. I know a lot about acoustic simulations and have this kind of draft of a new technology. Should we maybe do something with it? And he was willing to do that. So we started Treble 1.5 years ago, something like that. What Treble is we're calling it a platform. So it's a sound simulation and sound rendering platform. And when I say platform, I mean it's kind of consists of different modules that are tailored towards different industries. One maybe towards building industry, one towards automotive, one towards audio technology, but these kind of different use cases where we want to simulate and render sound and predict how things sound. Right, and I have a couple of slides here to elaborate a bit further. So when I say sound simulation, I think we kind of already covered this, but it's using these computing techniques to predict how things sound and then optimizing and designing on that further. And the rendering part is then to be able to, it's kind of builds upon the simulation, to be able to experience the simulation and ideally, interact with it on the fly, maybe walk around the space and so on. And I'll show you a demo of this later. Treble was founded in a windowless basement at the University of Iceland. We were kind of me and Jesper here originally, and then Gunnar and Ingimar came on board very quickly after, got a grant to get started and so on. But things started picking up quite rapidly. We got good investors to join us and sense a lot of interest from different industries in our tech. So we've grown quite a bit since this 1.5 year. This photo is actually already outdated. We have 5 more people since then. So things are going well, but we have not officially released a product yet, but we have started lots of different sort of partnerships with different companies and different industries. Are sort of starting to approach officially releasing here. So that's kind of the story that of how we got started and where we are today.
Okay.
Now I think I will just dive into the technology itself.
I said I'm a bit closer for this bit.
So when we do acoustic simulations, and that could be acoustics of a building, but also just like you described, an the simulation of a loudspeaker. What we do is we start with some input data, some geometry model of the 3D model of the geometry in question, or it can be a 2D model too in some cases. Some description of the acoustic properties of the boundaries of this model, and some way we excite the model. In a loudspeaker case, that might be some electromagnetic force, or in a room simulation, then we typically have some sort of model of the sound source, whether that's a human voice or human speaker or loudspeaker, or maybe just an omnidirectional sound source. We then feed this information to a simulation algorithm that computes how sound propagates in the domain in question, how it bounces off the walls or whatever, and reaches some listener position. And then the output of the simulation can be in different forms. It can be in the form of graphs and numbers, which can be important for all kinds of analysis work. Mm-hmm. We can also visualize sound, which can be useful in certain cases. Maybe we want to spot some echo patterns, for example, or investigate coverage or things like that. And then last but not least is this kind of rendering idea of being able to listen to it. And we did quite a lot of work here on the simulation part itself, developing a new approach here, and also on this kind of rendering stuff.
So that the graphic, the moving image on the site is kind of showing a time progression of a wave. Is that actually normally what you're doing, or is it more looking at a steady state type of behavior?
Yeah, no, we do this kind of time progression. Well, we do both, I would say. But time progression of looking at how sound propagates through the space, and also then some kind of more steady state parameters that describe the time average scenario. And
So I do headphones, and pretty much the entirety of it is considering things in a steady state form. So it's like a frequency response, frequency domain type of a thing. How important is that? I'll call it time domain, but you might have another phrase for it, that type of time series or progression of time information.
That can be quite important. In room acoustics, many kind of acoustic parameters or acoustic descriptors of the quality of acoustics are sort of time-based, comparing, for example, early versus late reflections or these types of things. And then also, especially for when it comes to the listening part, then we want to kind of convolve, ultimately that's a time domain signal that we hear. We convolve a time domain impulse response with some audio source signal, and then we can hear that source signal in the space. So we primarily simulate in the time domain, and then if we want to look at the frequency response, then we use a Fourier transform to look at that. But
it's the easy part, is it?
Yeah. But frequency domain approaches are certainly valuable too, and can be used as well.
Yeah.
All right. So when it comes to the simulation approaches or the simulation algorithms themselves, there have been a bunch of different methods proposed throughout the years. But they are typically divided into one of these two categories. On the right here, we have what's typically called geometrical acoustics, and on the left, we have what's often called the wave-based acoustics. And in geometrical acoustics, we employ quite a lot of approximations. We don't really solve sort of the differential equations involved using numerical methods, but we approximate that the sound wave behaves like a ray that sort of bounces around the room. It's often called ray tracing, following essentially the laws of optics. And what's attractive here is that this is a computationally light process. So back in the day, if you were simulating any kind of big domain, then this was absolutely necessary. You could never do this with computers of 20 years ago. But the drawback with geometrical acoustics is that sound does not behave like a ray. It behaves like a wave. So the accuracy can be low, especially when we have wave phenomena such as diffraction and interference and phase and scattering and these types of things, which tends to happen a bit more in the lower portion of the frequency spectrum, but still can happen across the board. That's one approach. And then the other approach is, which kind of has the opposite pros and cons. We solve the differential equations using numerical methods. So in principle, these should be very accurate methods. But the drawback is that the computational costs can be quite heavy. So what we set out to do was to improve wave-based methods, try to accelerate them and improve their accuracy so we can actually use them in practice.
When you say this computational costs are heavy, you instinctively feel who really cares, because you don't have to do it by hand, the computer does it, but it's not as simple as that. Is it
No,
get
I
to
mean,
it's at a level of it's just not possible?
yeah, kind of. I mean, imagine you're designing a space and you have to wait 3 weeks for a simulation result. And you do multiple iterations of your design. You try this thing and then no, it doesn't really work. I want to move the absorbers over here. No, it doesn't really work. Okay, what if we change the shape of the space? This kind of thing. And then you have to wait 3 weeks between each iteration. It just becomes very impractical,
Yep.
So that's the reason. But the sort of wave-based approach or the finite element, finite difference approach, has been viable in practice in industrial applications for smaller devices like loudspeakers or hearing aids or things like that. But anytime you come to a bigger space or bigger domain, then it becomes impractical, as I described before. But this is what we wanted to address. Can we, take these methods out of the academic world? They've been in the academic world since the 90s, essentially. But can we, put them to a place where they're actually useful in practice, bring the computation times down to something that is practical? And what we did was, together with these mathematicians I mentioned earlier, they've been solving wave problems for 20, 30 years, and we asked them, what's the best numerical method that we could use for this acoustic problem that we have to accelerate it? And they came back to us and proposed this method that has this very simple short name, discontinuous Galerkin finite element method, but often called DG or DGFEM, which is a kind of state-of-the-art numerical method that has these attractive features here that make it very well suited for acoustic simulations. And this is really the core of our technology is this numerical method. So it's very flexible in terms of geometry. We can simulate complex shapes and so on. And then this thing, high order accuracy, it basically means efficient simulations. And then last but not least, this thing here, which is that it's very well suited for parallel computing. And that means that we can use the sort of this awesome modern computing hardware that's been coming out for the last 10 years or so, which is these massively parallel computing cards or architectures to really accelerate the simulations. And the reason why it's so suited for parallel computing is, well, for traditional finite element methods, as most of COMSOL's functionality, for example, is based on, is then you have a mesh. So you discretize your loudspeaker or your room into kind of small elements. And each element on the mesh is kind of connected to every other element on the mesh. So the solution in one point depends on the solution in all points. Whereas in DG, I tried to illustrate it here with these figures, then each element on the mesh is sort of independent of each other. So you can solve them all in parallel for every kind of time step. And that's what makes it so powerful.
So basically you're breaking up the tasks and allowing multiple processors to calculate that all in parallel. That's
exactly.
All right.
That's exactly it. And we have these computing hardware now, these GPUs, graphics processing units that have thousands and thousands of cores, and then you can string together many GPUs as well. So you can really, when using the power of the cloud and these computing architectures, you can accelerate a lot.
Yeah, you just need to compete with the gamers and the Bitcoin miners to get those GPUs lately.
Exactly. And, this chip shortage and all that, we're actually feeling that, yeah. Okay, so some examples here of a couple, just to make this a bit more tangible, the numbers we're talking about, if we go from a CPU to a GPU using DG, then we can, speed up something like three orders of magnitude. And then these kind of very big spaces covering a large portion of the frequency spectrum, we can simulate them in, practical runtimes. It's still measured in several minutes, but this is definitely kind of usable in practice. So it's this combination of an advanced numerical method and advanced computing hardware that is really the core of Treble's technology. And it is, this is, for example, a recent study that some students did at DTU, where they're finding that it's something like 100 to 300 times faster than traditional simulation software for acoustic problems. And that is, that might sound like, okay, that's nice, but it is actually very nice, because it really opens up like a whole new host of applications, things that you couldn't really do before that you can do now. It's not that you can just do them a bit faster than before, but so that's quite exciting. And I'll show some examples of that towards the end. Okay, so I will move on. Another thing is, just to mention, another thing that we actually put a lot of effort into is material modeling, or sort of modeling the acoustics, the interaction between the sound wave and the surfaces in a room. That's because these surfaces, these absorbing conditions and so on, they have a huge influence on the acoustics of spaces. And it's actually can be at least for certain materials, quite complex physics that sort of interact when a sound wave hits a surface. So we did a lot of effort into this as well, and came up with some pretty advanced techniques here as well. And I have an example of an experimental validation of that as well.
Okay.
And then the last part is this whole rendering idea. So one thing is to be able to do the simulation and get out, the acoustic parameters or the frequency response or things like that, which certainly is valuable. But if we want to, for example, enable architects to understand the impact of different design options or clients even, then showing them a frequency response or showing some acoustic parameters maybe doesn't really do the trick, because they don't have a good feeling for what that means. So we developed this system that where we sort of use the high fidelity simulations in a kind of pre-computation stage, where we simulate the acoustics of a space. Here's an open plan office as an example, kind of in a grid across the space. So we've kind of pre-computed the acoustics all over here. And then during runtime, when people put on the VR headset, they can walk around the space, and what they're hearing then is kind of the nearest points being played back. And we have some pretty advanced signal processing stuff that kind of interpolates between the nearest points and decodes. We have embed spatial information into each response as well, so that, when you turn your head and so on, then the sound source is always kind of coming from the right direction and so on.
Mm-hmm.
And this way we can kind of couple the visual model and the acoustic model, walk around with it. We can interact, flip between different design options on the fly and so on.
That part of it strikes me as being vastly more complicated than a one-time simulation.
Right. I think that's fair to say, yeah.
Mm-hmm.
So you doing it in the sense where you inputting some signal, a sound, so someone's talking, and then running it through this algorithm, this real-time audio processor, and get the depend on your position and movement, you get a different output signal.
Yeah, exactly. Yeah. And in some cases it might be sufficient that you can just that you just get the result in one point in space, and you could but in others it can be nice to walk around, and especially if we start moving towards applications like video games and all kinds of VR applications, which are maybe not building design, but where you want to have this kind of authentic, properly simulated acoustics as a part of the experience, then this becomes quite necessary.
Yeah,
I wonder, if you think about rendering images, so if you're rendering one static image, and that can take quite a long time, even on a computer these days, you want to get high resolution, you can get something very realistic. But then if you want to have it rendered as a video, you can do that frame by frame kind of thing. But if you want to have that real time, it starts to degrade pretty rapidly. But visually seems kind of a bit more forgiving. If you're listening to something audio-wise, that degradation from like a single shot rendering to something that's real time. How does that turn out? I guess I'm wondering.
Right. There is definitely some degradation of the quality here when you go to real time. So this is actually, I mean, another approach to this whole problem is that you don't pre-compute the acoustics, but you actually also simulate the acoustics on the fly. So you do everything in real time, and there's tools that do this, and those tools are very, very approximate because
too much data.
Yeah, exactly. So what we've tried to sort of find the middle ground here by doing the acoustic simulation itself in an offline stage beforehand, which is then allowed to take some time, and then just the real-time processing of kind of interpolating between the nearest simulated points on the fly. And this works pretty well, I would say. We've done some listening tests on this, and people are able to point, for example, where sound is coming from in space very accurately, and so on. But a limitation of this is that you cannot really do moving sound sources. So you can remove the listener, but if you want to have a moving sound source as well, then the amount of data just kind of explodes. So that's something that we are working on right now to try and develop some approximate methods so that we can actually have the moving sound sources as well. Okay. Let me show you a couple of examples of some experimental validation to see how well this stuff works, and maybe give some sort of hint into the fidelity differences that we're talking about here. So the first case is actually the one that we're seeing right here. This is a measurement scenario where we have a sound source emitting a wave, and there's a direct sound that reaches the microphone, and then there is a reflection off of this sort of fairly complex geometric shape, kind of a diffuser, you could say. Pretty academic setup, or sort of a controlled scenario, but still can tell us quite a lot about how well, we can model complex geometry and sound propagation and interaction between geometry and the wave and so on. And this measurement is from a database called Ground Truth for Room Acoustic Simulations. It's coming from some university in Germany. I forget which one, but those guys who made the measurements, if you focus here first on the right here, so they when they made the measurements, they wrote a paper where they reported the measurement database, and then they also took a bunch of industry standard room acoustic simulation tools, which are all based on this geometrical acoustics paradigm, because that's what's really only available today is tools based on geometrical acoustics. And they tried to simulate these different cases, for example, this case that we just saw. And what you see here, you see the frequency response between the source and the receiver. So, we have the measurement curve here in black. There's all of these geometrical acoustics tools, they are not at all able to capture the frequency response here. And that is because they don't take into account the wave nature of sound, diffraction and interference and these things, which is very strongly happening when you have this kind of complex geometry.
I think the guy in dashed red line, he's already pretty happy that he's getting the peaks and dips.
Hey, right. Yeah, exactly.
The same number of them. Frequencies a bit off. Never mind.
Exactly. Some are better than others. Absolutely. And, and there are some, there's a ton of research done in sort of trying to improve geometrical acoustics methods to account for wave phenomena in some kind of approximate way. And those can be quite powerful tools. Don't get me wrong, but still, not perfectly hitting the response. But what we see here on the left is if we do a wave-based simulation, then we can capture this quite well. This is another example that we did where we simulated like a full room, so an impulse response of a room. It's a relatively simple room, but still we have this porous material here covering one surface, and tried some different material properties, and you can see the kind of match between frequency response and in measurements. This is just showing the low frequency response here, because if we go to higher frequencies, then and frequency response become kind of very noisy because you have more and more eigenfrequencies as you go up in frequency. So it becomes a bit hard to see whether there actually is a match or not, but it's kind of evident here in the low frequency range, at least.
Is it sort of understood where the discrepancies come from? I mean, let's say this is frequency on the x-axis, is getting higher in frequency. I guess there's some kind of spikes that don't really appear. Do you think, is it understood where those discrepancies come from?
I would say so. It's a limitation of the input data that we have.
Yeah.
So both the geometry, even though this is a simple geometry, I mean, it's just a box-shaped room, but it's not absolutely a perfect box. There's some tolerances in how straight those walls are and so on. So that can already start to have a small impact. And then I would say the biggest limitation is the material input data. So like I said earlier, it can be quite complex physics that describe the interaction between a sound wave and a material. And the data that we have today it's not quite good enough. I mean, it's getting better, and then there exists some models and so on, but this is a limitation.
So is it a tetrahedron or a dodecahedron speaker? Is that modeled as a point source, but in fact it's not really?
That's also a good point. Yeah, that's another source of limitations. We model that as a perfectly radiating, omnidirectionally radiating point source, but in reality, obviously, it's not. Maybe at the lower frequency range, it's somewhat close to that, but still, it's not.
So that's already a pretty incredible agreement of measured and simulation.
Yeah. So that's exciting. And then the last experimental validation is actually more kind of covering this material stuff. So we, for example, developed a method to model suspended porous materials. That might sound like a very niche case, but it is actually very common. These kind of, your typical acoustic ceiling, which is a kind of a suspended porous material, and then you have the ducts and everything above the ceiling. And that is actually very complex physics that occur there, because then you have this air gap and you have the panel kind of vibrating and so on. So we developed a method to model this very precise, or quite precisely, let's say. And we did some experimental validation of this, where we have a sound source here emitting a wave and hitting the surface and being reflected back, and at different incidence angles. So for a normal incidence angle, when it just comes straight in and straight out, then actually sort of existing methods and existing models are quite good. But as soon as you come to some higher incidence angle, then those methods break down. And that's because the sort of absorption behavior of this type of surface is actually very angularly dependent, so depending on where the sound wave is coming from, then you get very different absorption characteristics. And this is, as of today, not taken into account at all in room acoustic modeling. So here you can see some transfer functions again for different kind of incidence angles. And you see for the low incidence angle close to normal incidence, this is what's called local reaction, which is sort of the old traditional way of modeling this behavior. They match up pretty well with the measurement and with our what's called equivalent fluid model, which is the more advanced method. But when we come to higher incidence angles, then we start to see that the local reaction one doesn't really capture the curve so well. And the equivalent fluid model, it's at least closer. There's room for improvement. Sure, there's uncertainties in the measurements and so on, but it's a step in the right direction, let's say.
Yeah, capturing the broader characteristic.
Indeed.
Yeah.
Okay. We made it through the deep end of the pool, the deep dive of the tech, and I hope you're still with me.
Yeah.
Excellent. So I'm going to show you now some examples of how this can be used in practice. I've of course hinted a bit at some of the things already, but the obvious one being the building industry, that this is what we're targeting first, developing a simulation product for architects and engineers in that industry to be able to simulate the acoustics of sort of indoor spaces. But a natural next step is to start looking at outdoor sound. And and sort of, again, kind of relating to building design and urban planning and things like that. So it's kind of similar industry, but somewhat different use case.
And I just the previous slide in terms of, let's say, the concert hall or indoor spaces, somebody from the building industry, they would engage you guys to construct the model and produce the simulated result? Or you just sell them the software and they do it by themselves?
Yeah, it's more that, exactly. We develop the software, and then acoustic engineers in the building industry and architects should be able to use them by themselves.
Okay.
Interesting. So there's quite a lot then. I mean, I haven't really talked too much about that, but there's quite a lot in terms of the user interface of how to get a model into the simulation. That's not trivial as well, I guess.
Absolutely. And that's something that we're very much emphasizing, is to try and make that process as seamless as possible, because it can take a lot of time to clean up the geometry so it's suited for simulation and put in all the material properties and all these things. So we're trying to make that as seamless as possible, because the building models actually all have that information in them. It's just about kind of packaging it in the right way so it can be used.
And what kind of form are you talking about when the building models have it? Do they have 3D models? 3D CAD models of the entire building. You're aiming to try and just import that data.
Yeah, exactly. This is often called building information modeling, BIM models, where you have obviously the geometry, but then you have a bunch of metadata that goes along with it, material properties and things like that. And then we try and sort of extract all of that into a simulation model as automatically as possible.
Interesting.
When it comes to environmental noise, there are, again, some kind of geometrical acoustics-based tools available, and they're okay for their purpose. But for example, if we want to design the shape of a building so that it kind of shields away noise, and so you can have like a quiet courtyard or something like that, then kind of diffraction of sound waves becomes a very important aspect that you cannot really take into account with geometrical acoustics. Or if you're designing a noise barrier alongside a highway, then again, kind of how sound diffracts around, bends around the barrier becomes an important issue. So this is an exciting application, and it's somewhat similar to the indoor case, except indoors we have a very steady medium air, but outdoors we have weather that can have an impact. So it makes the physics a bit more complicated.
Right. So is that like the humidity and wind change could heavily? What kind of impact would that have on car noise? Is it massive or?
It depends a little bit on what sort of distances and sizes of domains we're talking about. If you're talking about 100 meters or less, then maybe it can almost be acceptable to just neglect those factors and just kind of assume that it's a calm, medium average day. But as soon as you're talking about maybe, measured in the hundreds of meters or beyond that, then it has a huge impact. Just easily 20, 30 decibels of level can change, depending on wind and temperature gradients and things like that.
Okay. Interesting stuff.
Another use case, which I think is very interesting, has to do with kind of audio signal processing techniques like speech recognition and echo cancellation and so on in these kind of smart audio devices, like meeting room equipment and all kinds of software where you want to ultimately capture an audio signal or remove the background noise and the echoes and so on, but capture the desired signal, typically speech. And these signal processing algorithms, I'm not an expert in those, by the way, but I'm aware that they are based on oftentimes on machine learning methods, where they train a neural network to distinguish between the desired signal and the background noise coming from a room. And the way that the companies work with developing this is this kind of that they, as of now, they either use measurements to train the the machine learning networks, or sort of very crude simulations. And this means that the performance is not as good as it can be. But with our technology, we can actually use or generate very high quality training data and a very big amount of it, which is not really possible with measurements. So we can hopefully improve the performance of these signal processing techniques.
That's a large market. I mean, there's lots of companies doing like SoundHound and I can't remember them all, but they're doing this training stuff to train the neural networks with voices. So so what you're saying is you could train the network for detecting reflections and different things in the room.
Exactly.
Okay, yeah.
And it's a very exciting field, and we've already started working with a few big names. I can't say who right now, but big names in this kind of this space. And
we can guess.
Quite excited. Exactly. And this kind of also this blind room acoustic modeling, which is kind of this inverse problem where you have some speaker might be able to measure a few discrete points measure a space in a few discrete points, and then it tries to reconstruct what the room is, and then you can take that information into account and adjust its settings and so on. This is a kind of an analogous use case where we could use lots of high quality training data to improve the performance of this.
Yeah,
that's very exciting. Then the world of personalized audio is another very exciting field, and I know there's quite a lot of companies working in this, but we can contribute here by being able to simulate HRTFs. So in a very both accurate way and a fast way. So we're, for example, working with a big hearing aid company where the objective is that once you buy a hearing aid and you go to the fitting process at the clinic, then the audiologist would scan your head geometry, and then that geometry can be fed to the cloud, to the Treble cloud, and we can in a few seconds simulate precisely how sound reaches your eardrums and get an HRTF and get that then back to you. So I think this is very exciting, and I know there are a couple of companies that are kind of doing similar things, but more kind of machine learning based to actually generate the HRTF. But this is very kind of physics based, so there's no, it's very accurate, I would say. Automotive industry is another exciting example. Where, and especially as cars become kind of coming closer towards being self-driving and so on, and the whole sort of entertainment aspect of cars and sound becomes a big selling point. So we can simulate car cabin acoustics very well, and sort of the interplay between the sound system and the cabin, and then hopefully down the road we would like to incorporate vibroacoustics as well, so you can take the whole noise aspect as well into account.
So I'm just curious in terms of the outputs from a simulation. So let's say you, taking the car cabin example, you set it up with the cabin and speakers, and you would, an output would be like the frequency response at each person's seated position?
Exactly.
Yeah.
Or you could oralize it, so you could simply, hear how it sounds to sit in the driver's seat, Yeah. Then you could tailor the audio system, to EQ against the frequency response, for example, things like that. Okay. And, people are already doing simulating cars to some extent, but what's attractive here is that we can do it 100 times faster. So that's exciting.
Okay. That makes quite a big difference, doesn't it, the speed? Because if you are doing something in an iterative fashion, let's say you're trying to find what's the right, I can put the speaker somewhere around here in the door, and if you can simulate very quickly until you zero in on the nice position.
Exactly. Yeah. And then I think, this is one of the last examples, large scale sound systems. There exist pretty good tools to simulate, how a sound system will radiate sound, but the sort of interaction between that sound system and the room, it's harder to predict that now. And especially in the low frequency range where people are trying to set up these kind of radiation patterns where you send the sound just to the audience area and not anywhere else. That's quite difficult to do today. But with our technology, we can go to these, actually handle these large cases and simulate the interaction between the two. So that's quite exciting. And the last one here is something that we've just sort of started to dip our toes into, but that is kind of this idea of being able to accurately render, video game environments and have them have as authentic sound as possible, or acoustics incorporated. And
that one strikes me as being a slightly different direction. I mean, the real-time rendering in video games, but there's some elements of what you're doing that are applicable.
Absolutely, I completely agree. And all those other cases I mentioned before I mentioned the video games, then it's very much about kind of precision and replicating reality and predicting reality and then optimizing that. Whereas in video games, there's this kind of level of artistic freedom that you want to incorporate as well. So of course you want it to sound as realistic as possible, but also have creative freedom. So it's a different ballgame for sure. But we're just sort of starting to see whether it makes sense for us to look into that as well. Okay, so let me end this with a couple of demos of this sound rendering stuff for kind of building design applications. So this space here, this is a new city hall in Uppsala in Sweden, where we did this together with Henning Larsen Architects, who I did my PhD with. This space is tricky from a sound perspective. It's very big. It has glass all around, glass ceiling, hard floor. It's open to the public, so people can walk through here. There's a cafe here and so on. So when we were designing this, they were when they were designing this, they were struggling a bit with the acoustics, both just where to get sound absorption into the space, but also to kind of understand how far do we actually have to go for it to be comfortable. So we constructed a virtual mock-up together with them of this space, and I will show you a video from it. And in the video, you can see the user walking around the space, and she can interact with the design on the fly. She can change how many sound sources are present in the room, what we call occupancy, the level of occupancy. She can turn the acoustic treatment on or off. So when they were actually designing the space, then they tried many different design options, but in the video, we just show kind of with and without acoustic treatment. And then she can clap to hear essentially the impulse response of the room. And then she walks into the auditorium where she's selecting different surfaces and kind of flipping between some predefined materials. So let's give it a shot. I hope it gives some insights into what this might look like.
Made up of words that come to me spontaneously, words that speak the honest truth. Expect from me nothing else, because I do not believe, fellow Athenians, that I should be appearing before you at my age, behaving like a child, trying to construct over-adorned speeches. This is the only thing.
And then towards the end, she was testing the sound isolation between the two spaces. All right, so yeah, that was an example.
And that's all being done real time. This is not a...
No, yeah, exactly. So we pre-computed the impulse responses kind of across the space, and then the whole kind of processing, everything else was done in real time. Yeah.
Wow. That's fantastic.
So one example of the sort of outcome of this work was that they ended up designing these wooden frames that were incorporated into every kind of glass element, window element of the facade, and they have the kind of dual function of both looking very good, but also being acoustic absorbers. So that was part of the treatment there. And then we also covered this kind of interior building here, this facade of that with some absorption as well. So it was a very nice example of, in my opinion, of what can happen when, you know, the architects actually get a feeling for the importance of the acoustics and the client as well, and so on. So that was a very nice outcome.
Is there a bit of a battle between the creative of the designers and when you start saying, can we change the material a bit? It's always,
of course. Yeah, absolutely. but you know, at least, you know, because I was working for a few years as an acoustic consultant before I did this whole simulation stuff, and then I was, you know, fighting architects with where my weapons were graphs and numbers, and that was not very effective. I can vouch for that. So this was a completely new kind of changed the conversation a bit, or quite a lot actually.
Yeah.
When they could actually hear it.
Yeah, I think because then they get that kind of gut feeling. Oh, my building's gonna feel like cold and echoey and not comfortable. It might look beautiful, but it won't feel comfortable. So yeah, it's an amazing tool.
Absolutely. Yeah. Okay, and then one more example, more sort of smaller space, an open plan office. Is a bit of an older demo, so you see the kind of user interface is a bit different, but it's a similar idea. You can see the user walking around, and then he's kind of flipping on and off various aspects of the acoustic treatment, you know, putting absorption in the ceiling or not, putting in these kind of partitions or acoustic furnishing and things like that. Let's give it a spin.
It's everything off, is it?
Yeah, right. Yeah, exactly. Right. So there you could hear both the acoustic ceiling played a pretty big role, and then the dividers, especially, you know, they helped a lot to sort of reduce the sound spreading from across the office, essentially.
I suppose that'd be kind of the first time anybody's ever heard that kind of A/B testing of with and without acoustic materials.
Right, exactly, yeah.
Definitely me.
Cool. All right, yeah, that's a pretty comprehensive introduction to what you guys do, and I think it's a fascinating category. It's like, you know, everybody's been into some kind of building that people think they can hold concerts in, especially, and it's just like it's like horrible. Like here in Hong Kong, the Asia Expo out by the airport, that's where the only building big enough to hold concerts, and it's horrible with the reverb in there. It's And so, yeah, like having a consultant come in and hey, here's how to fix it. But like we said previously, having some advanced knowledge on how it's going to behave with different kinds of events and such going on is really cool. All right, Simon, do you have any more questions?
I'm just curious. So the market for your product is actually kind of huge, then, isn't it? I mean, it's a big money industry too, isn't it?
Yeah, I mean, it's quite diverse also. I think that's what excites me a lot, is that actually, I mean, there is so many different use cases where you want to be able to predict how something sounds and use that to optimize or design things further and so on. So I'm quite excited about it, yeah. And if things go well, then I think there could be a market opportunity there.
Cool.
Fantastic. Thank you very much.
All right. So, yeah, we'll put the information on your website down in the comments or the info below. Of course, if anybody has any questions, we encourage them to shoot their comments, questions, give us, I always say, the love and the hate. Tell us what you thought we got right. Tell us what you think is wrong about it. And of course, like, subscribe and share, all that good stuff. So Finnur, thank you so much for joining us today. We really appreciate it.
Thanks for having me. It was great talking to you. Thanks for the great questions. And yeah, it was a lot of fun.
Okay. All right. Thanks, everybody.
Bye-bye.